So we have two vectors here. Vector A, it has a magnitude of 3, so the length of this blue arrow is 3. And its direction, it forms a 30-degree angle with the positive, I guess you could say the positive x-axis. I haven't drawn that here. And vector B has a magnitude of 2, the length of this arrow is 2, and it forms a 135-degree angle with the positive x-axis. And what I want to think about in this video, and maybe the next one, depends on how we do with time, is what is the magnitude and direction of the sum of these two vectors? What is the magnitude and direction of the vector A plus B? And I encourage you to pause this video and try to work this through on your own before I work through it. Well, to think about this, I'm going to decompose each of these vectors into their horizontal and their vertical components. So for example, vector A could be viewed as the sum of this horizontal pointing vector plus this vertical pointing vector. Another way of thinking about it, this horizontal vector, this right over here, this is going to be a scaled up version of the unit vector I. And so this is going to be something times I. And this vector right over here is going to be something times the unit vector in the vertical direction. The unit vector in the vertical direction might look something like that. Or let's see, if this is 3, then the unit vector, yeah, actually it would look something like that. So that's what the j unit vector looks like, and this is what the I unit vector would look like. So this is a scaled up version of it. So it's something times I, and this is something times j. And the same exact argument right over here. This is going to be something times the I unit vector, its horizontal component, and its vertical component is going to be something times the j unit vector. So what we really need to do is figure out the magnitudes of these horizontal and vertical components, and then we know how much to scale up I and how much to scale up j. So let's think through this a little bit. So this one might jump out at you immediately as this is a 30, 60, 90 triangle. So if this is a 30, 60, 90 triangle, then this side right over here is going to be half the length of the hypotenuse. So this is going to be half of 3, so it's 3 over 2. And this one right over here, let me do it in that same color. So this is going to be 3, that's not the same, that's a different color. This is going to be 3 over 2. And then this length right over here, this is going to be square root of 3 times the shorter side. So this is 3 times the square root of 3 over 2. I just took this and multiplied it by square root of 3. And once again, that just came out of 30, 60, 90 triangles. Now another way that you could tackle this is to use what you know about your trig functions. You can say, okay, I know this angle right here is a 30-degree angle. This is the opposite side. So you could say, well, the opposite over 3 is going to be equal to the sine of 30 degrees. Let me write this down. So, toa. Sine of 30 degrees is going to be equal to, is going to be equal to the opposite side over the length of the hypotenuse, over 3, or we could say that the opposite side, is equal to 3 times the sine of 30 degrees, 3 times the sine of 30 degrees. And if you put this in your calculator, sine of 30 degrees is 1/2. And so you're going to get 3/2 here. Similarly, for this side is adjacent to the 30-degree angle. So you could say cosine. Cosine is adjacent over hypotenuse. You could say that cosine of 30 degrees is equal to adjacent over the hypotenuse, or multiplying both sides by 3, the adjacent is going to be equal to 3 times the cosine of 30 degrees. Times the cosine of 30 degrees. And the cosine of 30 degrees, if you type it in your calculator, you're actually going to get some type of a decimal, but it's square root of 3 over 2. So 3 square roots of 3 over 2. And you can verify this if you like. So we see here sine of 30 is indeed 1/2, and cosine of 30, well, you get this kind of crazy decimal, but notice that is the same thing as square root of 3 divided by 2, the exact same value right over here. But we were able to figure that out just using what we know about 30, 60, 90 triangles. Now this triangle, you might say, well, what's the angle? What angles do we know about it? Well, this angle right over here, this angle right over here is, this is supplementary to this 135 degree angle. So this is a 45 degree angle. This is 90, so this is 45. So this is a 45, 45, 90 degree triangle. Now you could say that using the trig identities and what we did right over here, that this length is going to be the hypotenuse times the cosine of 45 degrees times the cosine of 45 degrees. And you could say that this length right over here is going to be the hypotenuse times the sine of 45 degrees times the sine of 45 degrees, using the exact same logic here. And as you get more practice with finding the components, you'll realize, okay, you take the hypotenuse times the cosine of this angle, you're going to get the adjacent side. If you do the hypotenuse times the sine of this angle, you're going to get the opposite side. But we could use this sine of 45 degrees. Once again, if you put it in your calculator, you get a crazy decimal, but we can figure that out. We know 45, 45, 90 triangles. Sine of 45 degrees is square root of 2 over 2. Cosine of 45 degrees is also square root of 2 over 2. So I know my writing is getting a little bit messy, and actually I should have done all of this in green. Square root of 2 over 2. So what's the length of that green vector? Well, it's 2 times square root of 2 over 2. That's going to be square root of 2. What's the length of this orange vector? It's 2 times square root of 2 over 2, so it's going to be square root of 2. So now we know the magnitudes of the component vectors, the horizontal and vertical components of each of these. So now we can write these out as the sum of these horizontal and vertical vectors. So vector A, we can write as square root of 3, or 3 square roots of 3 over 2 times I. That's this vector right over here. We've scaled up the I unit vector by 3 square roots of 3 over 2, plus 3 halves times j. That's this right over here is this vector right over here, scaled up version of the j unit vector. And if you add this orange vector to this green vector, you get vector A. Similarly, vector B is equal to the length of the horizontal component. And we got to be very careful. Its length is square root of 2, but it's going in the leftward direction. So we're going to put a negative on it, times I. If it was just square root of I is doing something like this, square root of 2 times I would look like that. So negative square root of 2 would point it to the left. So this is negative square root of 2 times I, and then we're going to have plus square root of 2 times j. And so now that we've broken them up in their components, we're ready to figure out what, at least broken up into its components, what A plus B is. So A plus B is equal to, well, it's going to be the sum of all of these things. So let me just write that down. So it's going to be that. So copy and paste that plus this. So let me just copy and paste it. And you're going to get that. But of course, we can simplify this. We can add the I unit vectors to each other. If I have 3 times the square root of 3 over 2i's, and then I have another negative square root of 2i's, I can add that together. So this is going to be equal to 3 times the square root of 3 over 2 minus square root of 2 times I. And then I can add this to this, and I'm going to get plus 3 halves plus square root of 2 times j. So it looks a little bit complicated, but we could type it into our calculator and get approximations of each of these two values, and then we could, and we essentially have at least a broken down into its components representation of A plus B. In the next video, we're now going to take this and figure out the actual magnitude and direction of A plus B.